Hello everyone, welcome to my section. Here we will talk about the poster paper, MUST-GAN Multi-Level Statistics Transfer for Self-Driven Person Image Generation. This video will follow the outline, including introduction, methods, and experiments. Let's get started. Firstly, this paper mainly talks about a popular task, person image generation, or pose transfer specifically. This task aims to generate a person image by given the source person image and the target pose. Typically, the training dataset used for the supervised methods needs to include the source person image, the target pose, and the source pose in some methods, and a paired person image in the target pose. However, such pairwise training sets are often difficult to obtain in the actual scene, and need to be collected and labeled manually. Because what we get directly on the internet are often single-person images. The previous work can be divided into these types in terms of training sample form. Our method uses a self-supervised training approach with minimal dataset requirements. As shown in the figure, during training, our method is trained with the purpose of image reconstruction, while in the inference, we are free to control the input pose and the input person image to generate a person image with corresponding attributes. To implement this self-supervised person image generation, we construct a decoupled model of person attributes. The overall framework of the model is shown in this slide. First, IA is the input person image. The human semantic segmentation map SA, and human pose map PA and PA-CON can be obtained using the human parsing model, and the human pose estimation model trained on other datasets. Using SA and IA, we can get images of various parts of the human body. The two inputs are then fed to the appearance encoder and the pose encoder, respectively. The pose encoder can extract only the pose information. In contrast, the appearance encoder needs to feed multi-level features into the MUST module to decouple the rich and valid appearance information further. Finally, the appearance and pose features are fused in the generator to reconstruct the original input person image. The MUST module is a key to the effectiveness of our method, and its process can be simplified to this figure. First, the multi-level features obtained from the appearance encoder are fed into the combination, channel attention layer, plus convolution layer, and plus statistic extraction layer to learn the more essential appearance attributes. The statistic extraction layer can obtain the global style from the feature maps and decouple the appearance and structure attributes. Then, the MLP network transforms the acquired statistic features to match the generator and improve the learning ability of the network. The pose-guided generator is used to fuse the appearance and pose features to reconstruct the input person image. It consists of many fusion modules in the form of resblock and upsampling layers. Finally, the whole network is trained adversarially to learn good attribute decoupling and fusion capabilities. The loss functions used in this method include adversarial loss, reconstruction loss, perceptual loss, and style loss. In the inference phase, we replace the input pose with the target pose to achieve pose transfer task. Our approach also shows good performance results compared to the current state-of-the-art supervision methods. We test the performance metrics of each model on the deep fashion dataset. Our approach achieves the best results among the unsupervised methods. In contrast to the supervised methods, our model's performance can also reach a high level. It is comparable to person image generation methods trained in a fully supervised form. In addition, when we replace a semantic part of the input person image, our method enables close-style transfer. This slide shows the generation results by changing the upper clothes and pants of the input person images. Of course, we can achieve both pose transfer and clothes-style transfer at the same time by fusing the two mentioned manipulations. To verify the generalizability of our model, we also perform wild data testing. We download some person images from the internet and test the inference on our trained model. The experimental results show that our method has a good generalizability. We are glad you watched this video and welcome your attention and discussion.